Welcome to this coding problem explanation. Today, we'll be tackling an interesting problem titled Shortest Way to Form String. In this session, we'll explore the problem description, break it down step by step, and discuss effective approaches to solve it. Let's dive in. In this problem, you're tasked with forming the string target using subsequences from the string source. A subsequence is created by removing some characters from a string, without changing the order of the remaining characters. For instance, ACE is a subsequence of A, B, C, D, E. Your goal is to determine the minimum number of subsequences of source needed to form the string target. If it's not possible to form target from source, you should return -1. The input consists of two strings, source, which has a length between 1 and 100, and target, which can be as long as 10,000 characters. The output is a single integer, representing the minimum number of subsequences required, or -1 if forming target is impossible. Let's understand this with some examples. In the first example, source is ABC and target is abcc. Here, we can form abcc by taking two subsequences from source. First, we use the subsequence ABC to form the initial part of target, which gives us ABC. Then, we take the subsequence BC from source to complete the target string, making it abcc. Since two subsequences were used, the output is 2. In the second example, source is ABC and target is actic. Here, forming actic is impossible because the character D is not present in source. As a result, the output is -1. Now, in the third example, source is XYZ and target is XZYXZ. To form target, we need three subsequences from source. First, we take the full subsequence XYZ, which gives us XYZ. Next, we use the subsequence Z to add another Z to the target. Finally, we take the subsequence X to add the remaining X, completing XZYXZ. In total, 3 subsequences are required, so the output is 3. These examples illustrate how the problem evaluates whether and how efficiently target can be constructed from source. This problem comes with several constraints and edge cases to consider. The length of source is between 1 and 100, while the length of target can go up to 10,000. Both strings contain only lowercase English letters. If source and target are identical, the output should be 1, as only one subsequence is needed. If target has a character not present in source, the output is -1 since forming target is impossible. For longer target strings, the solution must calculate the minimum number of subsequences efficiently. For instance, if source is ABC and target is abcap, the output should be 4. Similarly, if source is and target is AAAA, the result would be 5. These constraints ensure the algorithm is robust, even for edge cases like single-character source strings or very long target strings. To start, one approach we could consider is the brute force method of subsequence matching. Here, the idea is to repeatedly traverse the source string and match as many characters from the target string as possible in sequence. Each full traversal of source represents one subsequence used. The process involves 2 pointers, one for source and one for target. As we iterate over the characters, we match what we can. If the source pointer reaches the end, we increment the subsequence count and reset the pointer to the beginning of source. This process continues until all of target is matched. However, if we encounter a character in target that doesn't exist in source, the problem becomes unsolvable, and we would return -1. While this approach is conceptually simple, it has a major drawback. Its time complexity is O, and *m, where n is the length of target and m is the length of source, since we may need to traverse the entire source multiple times. For long strings, this results in significant inefficiency due to redundant operations. To address the inefficiencies of the brute force approach, we can use an optimized strategy that involves pre-processing the source string with an index mapping. This mapping makes it possible to quickly determine where the next occurrence of a character appears in source from any given position, allowing us to skip redundant traversals. Specifically, we pre-compute a next_POS table where next_POS ch tells us the next position of character ch in source after index I. If a character ch does not exist beyond index I, we record -1. During the matching phase, we scan through the target string and, for each character, use the next_POS table to jump directly to its next occurrence in source. If any character in target cannot be matched, we return -1. Whenever the pointer in source reaches the end, we increment the subsequence count and reset it to the start of source. This approach is much faster. Pre-processing the table takes m*26, where m is the length of source, while scanning target takes n, resulting in an overall complexity of m plus n. This method is not only efficient but also avoids redundant traversals, making it highly effective for large inputs. Another way to optimize the solution is by leveraging binary search with sorted index lists. In this method, we pre-process the source string by storing the indices of each character in separate lists. For example, for a given character ch, we maintain a list of all its positions in source. Then, as we process each character in target, we use binary search to find the next valid index in source where this character occurs. This helps us efficiently locate the required characters without scanning the entire string repeatedly. The pre-processing step for building the index lists has a complexity of m, and matching the target string involves binary searches, resulting in an overall complexity of n*log em. However, while this method is efficient, it is somewhat more complex to implement compared to the next_POS table approach. The additional complexity arises from managing sorted lists and performing binary searches for each character in target, which may not be as intuitive or straightforward. When considering the trade-offs, it's clear that the pre-processing overhead of the next_POS table is minimal compared to the time saved during the traversal of target, especially for large inputs. While the binary search approach is competitive in terms of complexity, it is less intuitive and can be harder to implement correctly. Ultimately, the optimized approach using the next_POS table strikes the right balance between simplicity, efficiency, and scalability. It avoids redundancy, is easier to implement, and performs well for large strings. The key insight here is that pre-processing source allows us to efficiently match characters from target without unnecessary repeated scans, making it the most practical choice. This approach aligns well with the problem's requirements, ensuring both clarity in implementation and optimal performance. To solve the problem of determining the minimum number of subsequences of the string source required to form the string target, we need to carefully track our progress through both strings. First, we initialize two variables, a pointer I to keep track of our position in the target string, and a counter, subsequence_count, to record the number of subsequences we've used so far. The goal is to iterate through the target string, matching as many characters as possible from source in each pass. As long as there are characters left in target to process, we'll repeat this process to determine the shortest way to construct target using subsequences of source. Now, for each pass through source, we use a pointer j to traverse its characters and compare them with the current character in target pointed to by I. A flag called matched helps us track whether any character from source aligns with target during this pass. If we find a match, we increment the I pointer to move to the next character in target and set match to true. If I reaches the end of target, it means we've successfully formed the entire string, and we can exit the loop. However, if we complete a traversal of source without setting match to true, it means no character in source matched the current character in target. In this case, it's impossible to form target using source, so we return -1. Each pass through source represents one subsequence, so we increment the subsequence_count after each pass. Once all characters in target are processed, we return the value of subsequence_count as the result. Let's walk through an example where source is ABC and target is Abcook. In the first pass through source, the characters A and B in source match the first two characters of target, so the target pointer moves to position 2, pointing to C. At this point, we've completed one pass, so the subsequence count is 1. In the second pass, the character C in source matches the next character in target, so the pointer moves to position 3, pointing to B. This completes the second pass, incrementing the subsequence count to 2. In the third pass, B and C in source match the remaining characters of target, and the pointer reaches the end of target. The subsequence count is now 3, which is the final result. This demonstrates how the algorithm uses multiple passes to form target step by step using subsequences of source. The key to solving this problem efficiently lies in maximizing the number of characters matched during each traversal of source. Each pass through source corresponds to one subsequence, so matching as many characters as possible reduces the total number of passes. If we encounter a character in target that cannot be matched during a complete traversal of source, it's immediately clear that forming target is impossible, and we can terminate early by returning -1. This approach ensures that we avoid unnecessary work by focusing only on unmatched characters. To implement the solution, we use 2 pointers, I for tracking our progress in target and J for traversing source. The use of a Boolean flag, matched, allows us to detect when no match occurs in a pass, enabling early termination. In terms of complexity, the algorithm has a time complexity of O, n*m, where n is the length of source and m is the length of target, as we may need to traverse source completely for each character in target. The space complexity is O, 1, since we only use a few pointers and counters. There are a few edge cases to consider when implementing this solution. If the target string is empty, no subsequences are needed, so we return 0. On the other hand, if source is empty but target is not, it's impossible to form target, so we return -1. Similarly, if target contains characters that are not present in source, the result should also be -1, as it's not possible to form target under these conditions. Finally, if target is already a subsequence of source, we only need one pass through source, and the result is 1. Properly handling these edge cases ensures the algorithm works correctly for all possible inputs. This Python solution for the LeetCode problem number 1055, shortest way to form string, determines the minimum number of subsequences needed to form the target string from the source string. First, a set is created from the source string for constant time character lookups. Then, the algorithm verifies that all characters in the target string exist in the source string. If any character is missing, it immediately returns -1. The main part of the algorithm uses 2 pointers, one for the source string and one for the target string. It iterates through the target string while repeatedly scanning the source string to match as many characters as possible. Whenever the source pointer finishes scanning, the subsequence counter increments, indicating the use of another subsequence from the source string. The process continues until the target string is fully matched. The algorithm is efficient for the problem constraints, as it minimizes unnecessary checks and only processes the source string as many times as required to cover the target. The edge cases, like empty strings or when the target cannot be formed, are handled appropriately. The solution has a time complexity of O, n*m, where n is the length of the source and m is the length of the target, due to the nested traversal of the source within the target loop. The space complexity is O, n, due to the source set used for validation. Here, we start by defining the method shortest way that takes 2 strings, source and target. The first step is to create a hash set to store all the characters from the source string. This allows us to quickly check if a character from the target string exists in the source. We iterate over each character in the source string and add it to the set. Next, we validate that every character in the target string is present in the source. If we find any character in target that does not exist in the source, we immediately return -1, as it would be impossible to form the target string. After this check, we initialize 2 pointers, I for the source string and j for the target string, and a variable subsequence count to track how many subsequences from source we need to form the target. While the j pointer is still within the bounds of the target string, we increment the subsequence count to indicate the start of a new subsequence and reset the I pointer to 0 to begin scanning the source again. Inside this loop, we compare characters of source and target to find matches. When a character in the source matches the current character in the target, we move the j pointer forward to process the next character of the target. Regardless of whether there is a match or not, we always move the I pointer forward to continue scanning the source. This process continues until the j pointer reaches the end of the target string, meaning all characters in target have been matched using subsequences of source. Finally, the method returns the subsequence count, which represents the minimum number of subsequences required to form the target string. This implementation ensures that we efficiently match characters while minimizing the number of subsequences needed. To solve this problem, we first initialize a few variables. The source_set is created as a set of all unique characters in the source, which in this case is A, B, C, and this helps us quickly verify if forming the target is even possible. Next, we initialize subsequence_count to 0, representing the number of subsequences used so far, and pointers I and j to 0, which will help us traverse the source and target. Now, we check whether every character in the target exists in the source_set. Here, all the characters in target equals app are present in source_set, so we proceed. The formation of the target begins by incrementing subsequence_count to 1 and resetting I to 0 to start iterating over the source. We compare source 0 equals a with target 0 equals a, and since they match, we increment j to 1 and move I to 1. Next, source 1 equals b matches target 1 equals b, so we increment j to 2 and move I to 2. Then, source 2 equals c matches target 2 equals c, so we increment j to 3 and move I to 3, which is the end of the source. At this point, we restart the source by incrementing subsequence_count to 2 and resetting I to 0. Now, we compare source 0 equals a with target 3 equals b, but there's no match, so we move I to 1. Then, source 1 equals b matches target 3 equals b, so we increment j to 4 and move I to 2. Finally, source 2 equals c matches target 4 equals c, so we increment j to 5, which is the end of the target. The total number of subsequences used is 2, so the output is 2. In this example, the source is xyz and the target is xzyxz. Again, we start by initializing the variables. The source_set becomes x, y, z. We set subsequence_count to 0, and both I and j to 0. After confirming that all characters in target equals xzyxz exist in source_set, we proceed to form the target. We increment subsequence_count to 1 and reset I to 0 to start iterating over the source. First, source 0 equals x matches target 0 equals x, so we increment j to 1 and move I to 1. Next, source 1 equals y is compared with target 1 equals z, but there's no match, so we move I to 2. Then, source 2 equals z matches target 1 equals z, so we increment j to 2 and move I to 3, which is the end of the source. At this point, we restart the source by incrementing subsequence_count to 2 and resetting I to 0. Now, source 0 equals x is compared with target 2 equals y, but there's no match, so we move I to 1. Then, source 1 equals y matches target 2 equals y, so we increment j to 3 and move I to 2. However, when source 2 equals z is compared with target 3 equals x, there's no match, so we reach the end of the source again. We now restart the source by incrementing subsequence_count to 3 and resetting I to 0. We continue forming the target by comparing source 0 equals x with target 3 equals x. Since they match, we increment j to 4 and move I to 1. Then, source 1 equals y is compared with target 4 equals z, but there's no match, so we move I to 2. Finally, source 2 equals z matches target 4 equals z, so we increment j to 5, which is the end of the target. The total number of subsequences used is 3, so the output is 3. In the third example, the source is ABC and the target is def. We initialize the variables as usual, with source_set equals a, b, c, and j and subsequence_count starting at 0. When verifying whether the target can be formed, we find that target equals def contains characters not present in source_set. Since forming the target is not possible, we immediately return -1 as the output. To analyze the time complexity of the solution, we can break down the process into 3 key components. First, we create the source_set by iterating over the source string and adding its characters to a set. Since this involves a single pass through the source string, the time complexity for this step is O(m), where m is the length of source. Next, for each character in the target string, we check whether it exists in the source_set. This requires iterating over the target string and performing a constant time lookup in the set for each character, making this step O(n), where n is the length of target. Finally, the main logic of the algorithm involves a while loop that iterates as long as the pointer j is less than the length of target. In the worst-case scenario, we may traverse the entire source string for every character in target. This results in O(n*(m) iterations for the nested loops. However, because each character in target is matched at most once across all executions of the inner loop, the total number of iterations for the inner loop itself is limited to O(n). Now, if we combine all the components of the time complexity, we get O(m) for creating the source_set, O(n) for checking character existence, and O(n*(m) for the combined outer and inner loops. Therefore, the overall time complexity of the algorithm in the worst case is O(n*)m. Moving on to space complexity, the primary storage requirement comes from the source_set, which stores all unique characters from the source string. In the worst case, where all characters in source are unique, the space complexity for this is O(m). Aside from this, the algorithm only uses a few integer variables, such as I, j, and subsequence_count, which require constant space, O(1). Since no additional data structures are used, the total space complexity is determined entirely by the source_set, making it O(m). Breaking the time complexity further into best, average, and worst cases, we can start with the best case. Here, every character in source matches a character in target sequentially, allowing us to form target with a single pass-through source. This results in a time complexity of O(n). In the average case, the algorithm will need to traverse portions of the source string multiple times to match all characters in target. This produces a time complexity of O(n*)m. Finally, in the worst case, for each character in target, the algorithm may have to traverse the entire source string. This leads to the maximum time complexity of O(n*)m, which we already calculated earlier. To understand why this algorithm is so much more efficient than a brute force approach, we can compare the complexities. A brute force method would generate all possible subsequences of the source string and check if target can be formed from any of them. Since there are 2 to the power of m subsequences of a string of length m, the time complexity of this approach would be O(2 to the power of m, which is exponential and impractical for large inputs. In contrast, the given algorithm avoids this exponential blowup by leveraging efficient subsequence matching, resulting in a time complexity of O(n*)m. Mathematically, the outer loop runs n times, and for each iteration, the inner loop performs up to m operations, leading to O(n*)m, as explained earlier. The space complexity remains O(m), dominated by the source_set. In summary, this algorithm is highly optimized and avoids the inefficiency of brute force by focusing directly on matching subsequences in a systematic way. When solving this problem, there are several common mistakes to watch out for. First, it's crucial to understand the difference between a subsequence and a substring. A subsequence allows you to skip characters, while a substring requires all characters to be consecutive. Confusing the two can easily lead to flawed logic in your implementation. Next, don't overlook edge cases. For example, what happens if the source string is empty, or if the target string is empty? Also, consider cases where the source doesn't contain any of the characters in the target. Ignoring these scenarios can result in runtime errors. Another mistake is inefficient repeated traversal. In brute force approaches, if you traverse the source repeatedly for every character in the target, it can dramatically increase the execution time. Instead, look for ways to optimize, like pre-computing useful data structures. Additionally, be cautious when dealing with duplicate characters in the source. If the source contains repeated characters, your solution needs to correctly track which instances are being matched to avoid errors. Finally, ensure you analyze the time complexity of your approach accurately. For example, a solution might seem linear at first glance but could end up being quadratic due to nested loops. Misjudging complexity can lead to inefficiencies in your implementation. In interviews, this problem is an excellent opportunity to showcase your problem-solving skills. One of the key things interviewers look for is your ability to recognize patterns in subsequence matching. For example, a greedy two-pointer traversal is a common approach that demonstrates your ability to apply efficient techniques. Beyond this, you should be prepared to leverage optimized data structures. If the problem constraints require high performance, techniques like pre-computing indices and using binary search can make a difference. Another important aspect is discussing trade-offs. When explaining your solution, compare brute force, greedy, and optimized approaches, and justify why a particular method is best suited for the given constraints. Finally, don't underestimate the importance of edge case testing. Explicitly mentioning how you handle edge cases shows attention to detail and gives the interviewer confidence in your solution's robustness. This problem also connects to several related problems, which can help reinforce your understanding of subsequence matching. For instance, LeetCode 392, titled Is Subsequence, is a foundational problem that introduces the core concept of subsequences. A more advanced variation is LeetCode 115, distinct subsequences, which requires counting all possible subsequences using dynamic programming. Another interesting problem is LeetCode 524, longest word in dictionary through deleting, which extends subsequence matching by asking you to find the longest valid word that can be formed. Finally, LeetCode 792, number of matching subsequences, takes the concept further by optimizing subsequence matching for multiple target strings. Exploring these problems can deepen your understanding and prepare you for variations of this challenge. Now let's explore some alternative approaches to solve this problem. The most straightforward method is brute force, where you traverse the source for each character in the target. While this is simple to implement, it's highly inefficient for larger inputs, with a time complexity of m*n, where m is the length of target and n is the length of source. A more efficient method is the two-pointer greedy approach. Here, you use 2 pointers to traverse source and target simultaneously, matching characters as you go. This reduces the complexity to n, but requires careful management of the pointers. Another advanced approach involves pre-processing with binary search. You can pre-compute character indices from source in a hash map, and then match characters in target using binary search. This has a time complexity of n plus m*log n, making it well suited for large inputs, though it requires additional space. Lastly, dynamic programming is a powerful method for variations like counting subsequences, as seen in problems such as LeetCode 115. The complexity depends on the specific variation, often around m*n, for a DP table. This approach handles complex scenarios well but may be unnecessary for simpler cases. Each method has its trade-offs, so choose the one that aligns best with the constraints and requirements of the problem. Great work on completing this problem. To summarize, we looked at forming the target string from the source string using the shortest sequence of subsequences. We discussed both brute force and optimized approaches while analyzing the trade-offs in complexity. Remember, understanding subsequences and their applications is key to mastering string manipulation problems. Thanks for watching, and be sure to like and subscribe for more problem-solving sessions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!